Mr. Taru, in this video we're going to do 3 examples of solving equations that have fractions in them, or in other words, rational equations. We're going to find timestamps in the description to jump ahead to each of these 3 examples if you would like to do that. You'll also find a link to my hundreds and hundreds and hundreds of math videos organized by subject, chapter, and subject matter, where I just said the same thing twice, covering Algebra 1, 2, Pre-Calculus, Trig, basically Algebra 1 to Calculus 2, and AP Statistics. So let's get started. When we go through this, I'm going to show us what I believe is probably the fastest technique of doing number 1 and number 2, which is preferred by many students and many teachers because, well, a lot of students struggle with fractions. So if you have trouble with fractions, aka division in your equation, the easiest thing to do is simply get rid of it. So we're going to do some kind of multiplication to basically eliminate the fractions that we see in number 1 and number 2. But though you may prefer that technique, it is not a good technique when you move from solving rational equations to rational inequalities. So we're going to look at number 3 a little bit differently. It may be a little bit of a longer process, but I want to give you another tool, another technique to solving these equations so that you have something that works when solving rational inequalities. The more tools in our toolbox, the better prepared we're going to be as we move through our journey of mathematics. So number 1. Now, anytime you solve an equation that has a math function in it that restricts the domain of that function, you need to be careful that when you finish and you get some answers and you're saying like n or x is equal to 2 and -5, that you don't have any what's called extraneous solutions. Basically, you've not found a solution that makes the original problem, well, undefined. So we do have, of course, division in this equation actually all over the place, which means that opens the door for there a possibility to be dividing by 0. Now I don't care if n or the variable itself is 0. What I care about is the expression in the denominator as a whole is equal to 0, because you can't divide by 0. So the first thing we're going to do is factor, might be a bit much for this particular one, but we're going to factor out the denominators and see that we have 1 over n times n plus 1 over n plus 1 over, that would be equals 1 over 2 times n times n. Maybe kind of silly here because we just have this factor of n raised to a first power and second power, but thinking about factoring out your denominators, or actually indeed anywhere that you see sort of polynomials expressions show up in your problems, you want to get that in factored form first, especially the denominators. So we have a factor of n in each of these denominators and a factor of 2. Well, you don't want any of these denominators, you don't want any of these factors of n to be equal to 0. So your domain is that n, let me put this in blue, n cannot equal 0. So your domain, well, that is your domain. N cannot be equal to 0. And you can have that written in a couple of formats, inequality format, interval notation, whatever your textbook is using. So now that we have our denominators all in factored form, what I'm going to do is, and what we're going to do together, we're going to multiply both sides of this equation by a combination of all of the individual factors that we find in the denominators. And that's going to allow us in the very next line write a version of this equation that has no division. So we have a factor of 2 here, and showing up in none of the other denominators. We have a factor of n in each of these denominators, but 2 of these denominators have an n squared. So we're going to multiply by 2 times n times n, or we're going to multiply both sides of this equation by 2n squared. And in doing so, we're going to have 2n squared times 1, which that would be 2n squared, but it would be over n squared. So we have, see here, and really now it's probably better not to see this as n times n, but as that original 1 over n squared. And the factor of 2n squared, that n squared, which is a factor of this expression, is going to cancel out with this n squared, giving us a numerator which is just equal to 2. But as I say this, I really want to write this 2n squared over n squared. Just as a teaching step, you may not want to write this particular line. we have 2n squared times 1, which is 2n squared over n. And then we have 2n squared times 1, which is, again, 2n squared over 2n squared. Well, I'm just writing this line for a teaching line to kind of show every single little bit of your work, because I just said we were going to multiply both sides by 2n squared and eliminate the fractions, the divisions, from our equation, creating another equation which is easier to solve, that you may find easier to solve. Well, any factor divided by itself is equal to 1. So n squared divided by n squared is 1, leaving us a factor of 2. We have one factor of n in this denominator. We have two factors of n in the numerator, that n times n. So that 1n is going to cancel out with one of those two, leaving us with just 1 in the numerator. And on the right-hand side, 2n squared divided by 2n squared is equal to 1. So what we really have here is 2 plus 2n is equal to 1. Now we have an equation, a linear function actually, with that variable of n only showing up once with a power of 1. So we're just going to now subtract both sides by 2, giving us 2n is equal to negative 1. And we're going to undo, like we undid this addition of 2 with the inverse math operation of subtraction, we're going to undo this math operation of a multiplication of 2 by dividing by 2. Okay, we've scared away the bad guys. Now, it's always a good idea with solving equations. The great thing about solving equations is it's really easy to make sure that you haven't made a mistake. Can you plug in an n value of negative 1/2 in each of the locations of n in the original equation and get the same answer on both sides? If you can, then you know that this is a correct answer. Secondly, we already determined the domain of the original function where n cannot be equal to 0, so we know that this is not an extraneous solution, and it is the actual correct answer. I'm not going to go ahead and take the time to check it, because, well, I already have. Okay, now moving on to example number 2. Say hi to the camera. This is our good girl, keeping us safe, but she's also interrupting the video. Okay, so here we've got another sort of equation, 2 terms on the left and 1 term on the right of our equation, and we're going to want to make sure with this division that we don't have any extraneous solutions in our final answer. So the r minus 2, that's already sort of like there's no factoring this first degree binomial. It's kind of already in factored form. But here with our second problem, are there factors with our quadratic expression, meaning that we just simply have a polynomial with a power of 2. We have a leading coefficient of 1. Now, I do understand that a lot of students do struggle with factoring, but as far as quadratics are concerned, whenever you have a leading coefficient of 1, that's kind of like the easiest that they're going to get. So when you go to factor r squared minus 7r plus 10, all you really need to ask yourself are, what are the factors of positive 10 that add to negative 7? And with a positive constant, your factors need to both have the same sign. Well, that's going to be r minus 5 times r minus 2. So we have 1 over r minus 2 plus 1 over r minus 2 times r minus 5, and that is equal to 6 over, again, that r minus 2. Now, as far as your domain, for the domain of our original function, we need to make sure that this expression of r minus 2, this factor, if you will, does not equal 0, so r cannot equal 2. And we also have a factor of r minus 5, so also r minus 5 cannot equal 0, so r cannot equal 5. So our domain for this original problem is that x cannot equal 2 and x cannot equal 5. If we happen to get one of these answers when we're done, we're going to have to throw it out because it's an extraneous solution. Just happened to come out through the algebra, but it doesn't solve the original problem. It actually makes it undefined. Okay, so we're going to just eliminate all the fractions. We're going to eliminate that division of the r minus 2 and eliminate that division of r minus 5 in the same step. So we're going to, I already have this kind of written here, probably kind of a bad spot, so I'm going to do is I'm just going to wrap the whole equation up and just, this isn't great notation honestly, but we're going to just show it on one side where we're multiplying by r minus 2 times r minus 5. Now when I take that grouping of factors and I multiply it to our first term, the r minus 2 is going to cancel, just leaving us with 1 times r minus 5. Now, this isn't so important because this is addition, but if it were minus, you would definitely want to, for our second term, open up a set of parentheses and, you know, allow that cancellation to happen as we multiply by whatever it is that we're multiplying by to get rid of this fraction bar. But if that were a minus sign, you would have to make sure that that gets distributed to, if there are more than one term, all the terms in this parentheses. The parentheses really aren't needed here because it is just addition, but also when you take r minus 2 times r minus 5, which is in the denominator, and you multiply it by r minus 2 times r minus 5, well, all of those factors are going to cancel out, just leaving us with, well, 1. So I'm showing a little bit less work than I did with our first example. Now, as we keep going, now we're going to do that r minus 2 times r minus 5 times 6 over r minus 2. Well, now that division of r minus 2 is going to cancel with the factor that I'm multiplying in, leaving us with just equals 6 times, I'm going to go ahead and write this. The r minus 2's are canceling out, so we have 6 times r minus 5. So we're going to go ahead and distribute this 6. If this were a number here or a negative, I would be multiplying that through the parentheses, but we have now r minus 5 plus 1 is equal to 6 times 1r is 6r, and 6 times negative 5, well, that's equal to negative 30. So we have a linear function that's got a variable showing up on each side of the equation, but I also have some like terms that I can add. So I'm going to bring together this negative 5 and positive 1 to give us negative 4. And a lot of students are really comfortable just moving the variables to the left side of the equation and all the constants or numbers to the right-hand side. In this case, and that's fine, I can subtract both sides by 6r and add both sides by 4, but I'm going to create a negative coefficient on the r, which I don't like to create if I don't need to. So we're going to, and I'm going to, for the matter of time, or space, excuse me, I'm going to subtract both sides by a 1r. And if needed, if you're making this kind of common mistake where you maybe subtract by r but forget to actually take anything away from the 6, you may want to just drop in that coefficient of 1 that's kind of basically invisible. You know, when you multiply by 1, kind of nothing happens, so we don't usually show it. If I'm moving my variables to the right-hand side of my equation, well, then I'm going to take my constant and move it to the left side. So I want to get rid of this negative 30 that's on the right side of the equal sign by adding both sides by 30. And we have 30 minus 4 is, of course, 26. We've got our 5r. We're going to undo that division of 5 by, we're going to undo that multiplication of 5 from the 6 minus 1 by dividing. So we're going to divide both sides by 5. And we get r is equal to 26 over 5. And let's just make sure that I have not made any kind of silly error. So we're good. This problem, if you plug it into where r is and you work out the arithmetic to check your work, you're going to get the two sides of your equation equaling the same numerical value. So we're good with that. It falls within the domain of our original function. The domain is all real numbers except 2 and 5, so we are good to go. Our answer is correct. Example number 3 coming up, well, right now. Example number 3, and yes, that a magically turned into an x. So we have x minus 2 over x plus 3 minus 1 is equal to 3 over x plus 2. Now, we're going to tackle this differently, and the reason is I want to give you a few skills that you're going to be needing when you move from solving rational equations to rational inequalities. See, when you solve rational inequalities, it is not a good idea, it is not effective to just, well, we're just going to multiply away all of those fractions. So what is that going to look like? Well, again, our domain, x plus 3 cannot equal 0. So x cannot equal negative 3, and x plus 2 cannot be 0. So x cannot equal negative 2. So if you get one of those two answers, just throw it out. It's extraneous. For this, what we're going to do is something that you already are probably doing when you solve quadratic equations. You don't sort of isolate the variable x. You set the equation equal to 0, and you factor it or complete the square or use the quadratic formula, something like that. That's what we're going to do here. We're going to rewrite this so that we have one fraction on one side of the equation, and it's simply set equal to 0. Not the fastest technique for this type of question, but useful in other types of problems. So on the left-hand side, we have two fractions, and we have our x minus 2 over x plus 3 minus 1 over 1. So what we're going to do is we're going to write this 1 over 1 with a common denominator of x plus 3. And I'm pausing because we have this x plus 2 over on the right-hand side, but we'll deal with that in a minute. We're going to write this as minus x plus 3 over x plus 3. And that's going to allow me to write the left-hand side as one fraction instead of two. And what are we going to have here? We're going to have x plus 2, that would be x minus 2, minus parentheses x plus 3 over now our common denominator of x plus 3. That's equal to 3 over x plus 2. We're going to distribute this negative sign, and that's going to give us x minus 2 minus x minus 3 over x plus 3 is equal to 3 over x plus 2. We're going to add like terms, and something kind of I'm starting to see a little bit nice happen here. We have x minus x is going to be 0, and negative 2 minus 3 is negative 5 over x plus 3 is equal to 3 over x plus 2. Now, what I have here really now is a problem that we could solve yet another way. We can see that we have one fraction on the left and one fraction on the right, and we can solve this by cross multiplication. So I'm not going to work it out this way because I'm thinking about you moving on to rational inequalities, but you could multiply both, cross multiply this now that we have a single fraction on each side, and have negative 5 times x plus 2 is equal to 3 times x plus 3, and you distribute away the parentheses, and you combine like terms if you have any, and you just kind of continue that process of solving that linear equation. So we're not going to do that cross multiplication. What we're going to do is set this equation equal to 0 by adding both sides by 5 over x plus 3. And that's going to give us 0 is equal to 3 over x plus 2, and then plus 5 over x plus 3. And when we're looking at this and setting it equal to 0, and thinking about a tool that is going to be useful for those rational inequalities, we need to get each side of the we need to get the right-hand side of this equation to be one single fraction. And we're going to do that by multiplying this 5 over x plus 3 by x plus 2 over x plus 2, a form of 1 that's going to change the look of this fraction but not its value, and this by x plus 3 over x plus 3. And that's going to be 0 is equal to 3 times x is 3x. 3 times 3 is going to give us a plus 9. And then positive 5 times x and then times 2 is going to give us a plus 5x plus 10. And that's all going to be over x plus 3 times x plus 2. And there's no reason to multiply these factors out in the denominator, a, because we're not going to work with the denominator for the rest of our problem. And even if we were solving a rational inequality, we would want that denominator left in factored form to make it easier to find the values that make it equal to 0. We're going to add the like terms in our numerator and have 0 is equal to 5 plus 3, which is 8x plus 19, coming from the 9 plus 10, over that denominator left in factored form of x plus 3 times x plus 2. Now, with us only needing this fraction, this equation, to now equal 0, the only way that's going to happen is if the numerator is equal to 0. So we have 8x plus 19 is equal to 0. We have 8x is equal to negative 19 after subtracting both sides by 19. And then dividing by 8, we're going to have our final answer of x is equal to negative 19 over 8. A value which is not extraneous, because the only restrictions on our domain is that x cannot equal negative 3 and x cannot equal negative 2. Now, yes, the first two problems we did were much quicker. Yes, once we decided, oh, let's this time add our two fractions on the left-hand side, whenever you have one fraction equal to one fraction, you can solve that with cross multiplication. But this extension where we're getting it set up so that this original problem is written such that we have a single fraction equal to 0, well, if we were comparing it to an inequality where it was having to be greater than or less than 0, or maybe an equal sign, like greater than or equal to, with those kind of problems, this is important because we have to set the numerator, and the denominator equal to 0, find critical values that we identify along the x-axis, creating intervals, and then we just simply test each of those intervals between the critical values of where the numerator and denominator equal to 0, and compare them to whether we're trying to see if this is greater than or less than 0, or greater than or equal to, or something like that. Here, where we're just solving rational equations, we're only looking for that numerator equal to 0. We have our final answer. Now, this is not the quickest way with our last example here, but now instead of having one tool for solving rational equations, you have 3 and your choice. I'm Mr. True. Bam! Go to your homework.